Hi, everyone. Thank you for having me here. It's a pleasure to present in this conference. Yeah, so I'll be telling you about precision cosmology with CMB lensing from ACT. As probably all members of the audience know here and from their previous talks, there's a huge amount of information found in the distribution of mass and in particular dark matter. And a very clean way to extract this information is through gravitational lensing. So I won't be talking about weak lensing from galaxies like Alex, but I will be focused on a particular source, the CMB itself, to study weak lensing. So the CMB is very clean for gravitational lensing because, one, we understand its physics very well. So it's very well-behaved linear physics. It has been mapped to exquisite precision. We also understand its redshift is coming from, so it's a single plane redshift 1100. But probably most importantly, it is the furthest light source we can see, and therefore, as the photons travel towards us, it's sensitive to all the mass in projection. How do we measure these effects? So the observable we are after is this lensing potential, the gradient of the lensing potential, the deflection field, which tells you the direction from which the CMB is emitted to where it's ultimately received. And you can see from this simulation here, going from lens to lens, that it's a very small effect. And the key point is that it introduces new correlations in the CMB that we can really take advantage of high-resolution CMB measurements to capture these correlations and reconstruct the underlying dark matter field. So these large-scale lenses inducing small-scale correlations. So we're talking about precision cosmology. So what we do with this lensing map is that in order to infer cosmological parameters, we take the power spectrum of this map. Yes, so we take the power spectrum of the map to get the lensing power spectrum, which shows how much lensing there is on the y-axis as a function of angular scale. So this shape may be very familiar to you because it's essentially the matter power spectrum in projection. And therefore, it's sensitive to many interesting cosmological parameters. So any sort of physics which affects structural growth will show up in this power spectrum. And in particular, we can answer these questions related to the sigma A tension. So in terms of these very interesting cosmological parameters. And here I will just show you in this work constraints, 2% constraints, which with systematics that are independent of Planck and other galaxy weak lensing measurements. So first, I'll show you our team. So this is part of the Atacama Cosmology collaboration. And in the work I will present today, led by myself, there's also a lot of input from Cambridge IOA, highlighted here. So the Atacama Cosmology Telescope was an Archimedes telescope located at the peaks of the Chilean deserts. So as of now, this was already a former telescope. It has been already dismantled and shipped away to give space for the Simons Observatory. But luckily, it has provided us with a lot of exquisite data sets that we have been start analyzing and finish analyzing now. In particular, you can see here the advantages of having these ground-based Archimedes resolution telescopes in this transition going from Planck to ACT plus Planck. It really adds to the small scales, such as you can see these red point sources from AGN, and there are also blue sources from TSZ. But the important thing here for lensing is that this is not only a high resolution data set, but it covers half of the sky. So we can just go from here to these very large, high fidelity lensing maps. So the maps here have been filtered in a way so that you are really seeing real structures at a particular direction in the sky. So these are real dark matter structures that I'm pointing. You can zoom into this map a bit more. So here is a cutout, and this is filtered in a different way, but again, you're seeing signal-dominated modes. But you kind of have to trust me for this because I'm saying that this is dark matter, but it would be good if I can really show you that these are the structures. And what's good is because these are high-fidelity maps, you can expect to see the correlation it has with other large-scale structure tracers. And it turns out a very highly correlated tracer is the cosmic infrared background. So at the independent measurement of these dusty emission galaxies from Planck, we can filter in the same way and overplot the contours. And hopefully you can see a very good resemblance even by eye. So perhaps it's not surprising that the luminous matter follows or traces the underlying dark matter distribution, but it's still very reassuring to see this by eye. So back to a bit more concrete cosmology. probably the main challenge of this work was not just measuring the spectrum, but given the high signal-to-noise we are trying to achieve and the stakes about structure growth we are trying to say, how can we really trust these measurements? And luckily, the ACT dataset provides a huge lever arm in terms of null tests we can design so that we can check very carefully all the things we are worried about and pass all the tests in a blended framework so that we can really trust our results. So here I will just show you the cosmology we're getting here after passing all the null tests. This is the lensing spectrum as predicted from the Planck based on the lambda CDM model that we are trying to compare results to. So we have been doing this analysis blinded in the dark for 3 years. And then once we pass the null test, we jump into this Zoom call in this nerve-wracking moment, and we plot our measurements for the first time. So we were not allowed to do this for a long time. So these are our results here in red. You can see that it agrees very well with the lambda CDM model with a PT of 0.17. So just reminding you again that this black curve here is not a fit, but the actual prediction. Despite the high signal-to-noise, it agrees very well with these predictions. So George probably will be sad about this because even with this high signal-to-noise dataset, we are not able to break lambda CDM. But I think it's worth thinking how challenging or how many things you need to get right for this agreement to happen. So first, you need to fit your lambda CDM model based on the CMB at early times, right? And then you need to predict over billions of years how the structure forms, and then how this dark matter will lens the CMB, what kind of trispectrum it produces. And then with a completely independent experiment from ACT, we can measure this and show this remarkable agreement. 5 minutes, okay, perfect. And here is putting these measurements into context. So in red, that's our measurement. And you can see from this plot is what is nice because we are after the same observable, we can put them in the same figure and compare them. And you can see that our measurement is the highest signal-to-noise alongside with Planck in blue. And we are generally better in smaller scales, and these measurements are all consistent with each other. It's worth also noting that this evolution of these measurements happened in the span of around 10 years. So the first measurements in red was done by Blake around in 2011. In 10 years, we get to these precision probes of cosmology. So it's very interesting to, this is just getting started as precision probe, and it will be very interesting to see what happens in the next 50 years. So probably in the centenary talk of IOA, we'll show further results. So back to some more concrete cosmology, perhaps not surprisingly, our best constraint direction, this SA-CMB lens, agrees very well with these predictions from CMB. And in terms of these insights on structure growth, it's worth noting that despite reporting A8, all these measurements are sensitive to the different scales and ratios. And what CMB lensing is best at is at these high ratios and large scales. And the insight from ACT in terms of structure growth is that everything agrees very well with lambda CDM. But as Alex said, and the previous speakers, it's probably doesn't mean the other measurements are wrong, but it is very interesting in terms of this space that we're constraining and what future experiments can provide. A more slide in terms of other cosmology we can constrain. So ACT lensing can really help in terms of the neutrino mass because any suppression in the matter power spectrum is translated into CMB lensing. And you can see here that from ACT DR6, it's really adding or pushing to this very interesting bounds in neutrino mass, constraining that to 0.13 electron volts with both PAO, or these DESI results with 0.072. So this is already a very interesting regime. And here I'll just share with you the summary slides where all these lensing maps, they're available online for you to play or talk to me if you want to do interesting cosmology with this. And thank you very much.
Thanks very much, Brian.